CFA Level 1 Practice Questions. Learning Module, Hypothesis Testing. Topic: Hypothesis Tests for Finance. An economist believes that the average annual inflation rate in a country has risen above the central bank's target of 2%. She wants to test whether the population mean inflation rate exceeds 2%. Designating the population mean as mu, which hypotheses are most appropriate for her analysis? A. H0. Mu equals 2% versus HA. Mu does not equal 2%. B. H0. Mu is less than or equal to 2% versus HA. Mu is greater than 2%. C. H0. Mu is greater than or equal to 2% versus HA. Mu is less than 2%. An economist believes that the average annual inflation rate may have changed from the central bank's target of 2%, but is uncertain whether it is higher or lower. Designating the population mean as mu, which hypotheses are most appropriate for her analysis? A. H0. Mu is less than or equal to 2% versus HA. Mu is greater than 2%. B. H0. Mu is greater than or equal to 2% versus HA. Mu is less than 2%. C. H0. Mu equals 2% versus HA. Mu does not equal to 2%. Which of the following statements regarding the formulation of the null hypothesis is most accurate? If the null hypothesis may be expressed without including an equality sign. B. The null hypothesis must include an equality condition, such as equals is less than or equal to, or is greater than or equal to. C. The null hypothesis always represents the researcher's preferred conclusion. If a researcher conducts a hypothesis test using a 1% level of significance, the corresponding confidence level is A. 99%, B. 1%, C. 95%. Which of the following best describes a type 2 error? A. Rejecting a true null hypothesis. B. Failing to reject a false null hypothesis. C. Correctly rejecting a false null hypothesis. An analyst is testing whether the average return on a mutual fund is equal to the benchmark return of 6%. In reality, the fund's true mean return is 6%, but the analyst's sample evidence leads her to reject the null hypothesis that mu equals 6%. This situation is best described as an example of a type I error. B. A type 2 error. C. Correctly rejecting the null hypothesis. In hypothesis testing, choosing a 10% level of significance, alpha equals 0.10 means that the researcher is A. Defining the probability of making a type 2 error. B. Setting the rejection threshold, such that 10% of the distribution lies in the rejection region. C. Determining the width of the confidence interval used to estimate the population parameter. A medical researcher is testing a new drug. The null hypothesis states that the drug has no effect on recovery time. In reality, the drug does reduce recovery time, and the researcher's statistical test correctly rejects the null hypothesis. The probability of this correct decision is best described as the significance level. B. Type 2 error. C. Power of the test. The power of a test is best described as the probability of A. Rejecting the null hypothesis when it is true. B. Failing to reject the null hypothesis when it is false. C. Rejecting the null hypothesis when it is false. In the steps stating a decision rule in testing a hypothesis, which of the following elements must be specified? The significance level and the critical values of the test statistic. B. The sample statistic and its standard error. C. The confidence interval and the population parameter estimate. In hypothesis testing, the comparison of a calculated test statistic with a critical value is used to decide whether to A. Reject the null hypothesis. B. Accept the null hypothesis. C. Confirm the alternative hypothesis directly. An investment analyst is testing whether the average quarterly return on a sector ETF is greater than 2.5%. She formulates the hypotheses, selects a 5% significance level, and calculates a test statistic of 2.103. The critical value for the test is 1.729. Which of the following best describes the role of the test statistic in this hypothesis test? A. It determines the probability of making a type-by error. B. It provides an estimate of the population mean quarterly return. C. It serves as the basis for deciding whether to reject the null hypothesis. An equity analyst is testing whether a stock's mean return differs from 6%. She is particularly concerned about the test's ability to detect when the true mean is not 6%. The probability that the test will achieve this is best described as a complement of the probability of failing to reject a false null hypothesis. B. Probability of rejecting a true null hypothesis. C. Inverse of the significance level, 1 divided by alpha. Which of the following statements about the null and alternative hypotheses is most accurate? If the null hypothesis always represents the outcome a researcher hopes to prove. B. The null and alternative hypotheses together must include all possible values of the parameter under study. C. The alternative hypothesis is accepted as true unless the sample provides evidence to the contrary. One-tailed hypothesis tests assess if a population parameter is greater than or less than a hypothesized value. The economist's suspicion that inflation exceeds 2% necessitates a one-tailed test, with the alternative hypothesis stating inflation is above 2%, and the null hypothesis stating it is at or below 2%. Option A, two-tailed test. This would only be appropriate if the economist suspected inflation could be either higher or lower than 2%. Option C, wrong direction. It tests whether inflation is less than 2%, which contradicts the economist's belief. Use one-tailed hypotheses when the suspicion is directional, greater than or less than. Use two-tailed hypotheses when testing for any deviation, not equal. This is a two-tailed test because the economist is uncertain whether inflation is higher or lower than 2%. Null hypothesis, H0. Inflation equals the target, mu equals 2%. Alternative hypothesis, HA. Inflation is different from the target, mu does not equal 2%. Two-tailed tests are used when the concern is any change in either direction, not just one. Option A, one-tailed right-sided test, only checks if inflation is above 2%. Not suitable because the economist is unsure of direction. Option B, one-tailed left-sided test, only checks if inflation is below 2%. Also not suitable because the economist is unsure of direction. Use one-tailed hypotheses when the suspicion is directional, greater than or less than. Use two-tailed hypotheses when testing for any deviation, not equal. The null hypothesis must include an equality condition, such as equals, less than or equal to, and greater than or equal to, because it serves as the benchmark or default assumption. This ensures the hypothesis is mathematically testable and defines a clear rejection region. H0 is always expressed with equality, while HA states the suspected difference or direction. H0 assumes equality, while HA expresses the researcher's suspicion. H0 is the default assumption, not the preferred conclusion. The confidence level is always the complement of the significance level. Confidence level equals 1 minus significance level. At significance level equals 0.01, 1%, the confidence level is 0.99 equals 99%. Significance level represents the probability of a type-by error, while confidence level represents the probability of correctly not rejecting the null when it is true. Option B, this is the significance level itself, not the confidence level. Option C, A 95% confidence level corresponds to significance level equals 0.055%. Not significance level equals 0.01. A type 2 error occurs when a researcher fails to reject a null hypothesis that is actually false. This is a false negative because the test misses a real effect or difference. The power of a test equals 1 minus probability of type 2 error, probability of correctly rejecting a false null. Option A describes a type I error, rejecting a true null hypothesis, also called a false positive. Option C represents a correct decision, known as the power of the test, probability of correctly rejecting a false null hypothesis. Mutual exclusivity. Type I and type 2 errors are mutually exclusive. Only one type of error can be made in any single decision. The only way to reduce the probabilities of both types of errors simultaneously is to increase the sample size, n. The true mean return is 6%, so the null hypothesis, mu equals 6%, is true. The analyst rejected this true null hypothesis, which is the definition of a type I error, false positive. Type I error equals rejecting a true null. Option B, type 2 error occurs when a false null is not rejected, false negative. Not the case here since the null is true. Option C, correctly rejecting H0 applies only if H0 were false. Here H0 is true, so rejecting it is incorrect. Choosing a 10% significance level, alpha equals 0.10 means the researcher is setting the rejection threshold, so that 10% of the sampling distribution lies in the rejection region. Significance level defines the probability of a type I error, rejecting a true null. Option A misstates alpha. Type 2 error probability is beta, not alpha. Option C, while confidence level equals 1 minus significance level, the width of the confidence interval also depends on sample variability, not just significance level. The power of a test is the probability of correctly rejecting the null hypothesis when it is false. In this scenario, the drug truly reduces recovery time. Null is false, and the researcher correctly rejects the null. Power equals 1 minus beta, where beta is the probability of a type 2 error. Option A, significance level, is the probability of a type I error rejecting a true null. It does not measure correct decisions. Option B, type 2 error, is the probability of failing to reject a false null, false negative. This is the opposite of what happened here. Type I error, rejecting a true null, false positive. Type 2 error, failing to reject a false null, false negative. Power, 1 minus beta, correctly rejecting a false null, true positive. To increase power, researchers can increase sample size, reduce variability, or adjust alpha, though raising alpha increases type I error risk. Power of a test equals probability of rejecting the null hypothesis when it is false. Defined as 1 minus beta, where beta equals probability of a type 2 error. Power measures the test's ability to detect a real effect. Option A, rejecting a true null equals type I error, false positive, probability equals alpha. Option B, failing to reject a false null equals type 2 error, false negative, probability equals beta. In the 6-step framework, alpha is set in step 3, while step 4, decision rule, specifies the critical values that define the rejection region. The decision rule is about identifying the cutoff points for rejecting H0, not about calculating statistics. Option B, sample statistic and standard error are inputs for computing the test statistic, not the decision rule itself. Option C, confidence intervals can be used as an alternative approach, but the formal decision rule is based on critical values tied to alpha, not directly on confidence intervals. Hypothesis testing compares the test statistic to the critical value at a chosen significance level. If the test statistic exceeds the critical threshold, reject H0. If not, fail to reject H0, never accept H0. The decision rule is always framed as reject or fail to reject H0, not accept or confirm. Reject H0. Evidence is strong enough to conclude the null is unlikely. Fail to reject H0. Evidence is insufficient, but this does not prove H0 true. Support for HA comes indirectly from rejecting H0, never directly confirmed. Hypothesis testing language must be precise. You never accept H0 or confirm HA. The test statistic is standardized evidence from the sample. Its role is decision-making : compare it to the critical value or compare the p-value to alpha. In this case, since 2.103 is greater than 1.729, the null hypothesis is rejected at the 5% level. Option A, type I error probability is set by significance level before the test, not by the test statistic. Option B, the sample mean estimates the population mean. The test statistic is not an estimator. It is a standardized measure for hypothesis testing. Sample mean, point estimate used to inform about a population parameter. Test statistic, a calculated quantity from the sample, serving as the basis for deciding whether to reject or not reject H0. Significance level alpha, probability of a type I error, rejecting a true null. Critical value, the rejection point. If the test statistic is more extreme, the result is statistically significant. P-value, the smallest level of significance at which H0 can be rejected. Decision rule. If test statistic is greater than critical value, reject H0. If p-value is less than alpha, reject H0. Don't confuse. Alpha equals error probability. Sample mean equals estimator. Test statistic equals decision tool. The analyst's concern is about the power of the test, the ability to detect when the true mean is not 6%. Power equals 1 minus beta, where beta is the probability of a type 2 error, failing to reject a false null. Power is the complement of failing to reject a false null hypothesis, not type I error or an inverse of alpha. Power, 1 minus beta. Probability of correctly rejecting a false null hypothesis. Type I error, alpha, rejecting a true null hypothesis, false positive. Type 2 error, beta, failing to reject a false null hypothesis, false negative. Power is desirable when close to 1, and it increases with larger sample size, lower variance, and stronger effect size. The null, H0, and alternative, HA, hypotheses must be mutually exclusive and collectively exhaustive, meaning they cover all possible values of the parameter under study. This ensures every possible outcome falls under either H0 or HA, creating a complete decision framework. Option A, incorrect because H0 is not what the researcher hopes to prove. It is the default assumption the researcher usually aims to reject. The hoped-for condition is expressed in HA. Option C, incorrect because the statement accepted as true unless the sample provides evidence to the contrary actually defines the null hypothesis, not the alternative. HO is only supported indirectly when H0 is rejected. Null hypothesis, H0, baseline statement considered true unless evidence shows otherwise. Alternative hypothesis, competing claim, often the researcher's hoped-for outcome, supported indirectly when H0 is rejected. Topic: Tests of return and risk in finance. A pooled estimator is used when testing a hypothesis concerning them. A difference between two populations means when variances are assumed equal. B difference between two populations means when variances are not assumed equal. C difference between two population variances. An analyst wants to evaluate whether a training program improved analysts' forecasting accuracy. She compares each analyst's forecast errors before the program and after the program. The most appropriate hypothesis test to use is A two-sample z-test, B chi-square test for independence, C paired comparisons test. A chi-square, chi-2 test is most appropriately applied to test hypotheses about A, whether the variance of a population equals a hypothesized value. B, whether the means of two populations are equal when variances are assumed equal. C, whether the means of two populations are equal when variances are not assumed equal. Which of the following tests is most appropriate for determining whether the variances of two independent samples of stock returns, both drawn from normally distributed populations, are equal? A z-test, B f-test, C chi-square test. An analyst collects the following paired data, sample A and sample B, dependent samples, normally distributed populations, unknown variances. Observation 1, A equals 15, B equals 12, difference equals 3. Observation 2, A equals 20, B equals 17, difference equals 3. Observation 3, A equals 18, B equals 22, difference equals -4. Observation 4, A equals 25, B equals 21, difference equals 4. Observation 5, A equals 10, B equals 8, difference equals 2. The t-statistic to test the hypothesis that the mean difference is equal to 0 is closest to 1.11, B 1.435, C 1.775. Independent samples are drawn from two normally distributed populations. Sample A, n equals 30, mean equals 150, standard deviation equals 40. Sample B, n equals 20, mean equals 140, standard deviation equals 50. Assume the variances of the underlying populations are equal. The pooled estimate of the common variance is 1,850. The t-test statistic appropriate to test the hypothesis that the two population means are equal is closest to A 0.74, B 0.81, C 1.55. Samples of size N1 and N2 are drawn from two independent, normally distributed populations Y1 and Y2. Sample means Y hat1 and Y hat2. Sample standard deviations S1 and S2. Population means mu1 and mu2. Population variances, unknown but assumed equal. The most appropriate test statistic to determine if the two population means are equal is. Over the past 24 months, a bond fund's monthly returns have shown a standard deviation of 3.8%. An analyst wants to test the claim that the fund's investment strategy results in a standard deviation of monthly returns equal to 4.0%. The value of the test statistic is closest to 20.76, B 22.00, C 23.45. Using the following sample results drawn as 16 paired observations from their underlying distributions, test whether the mean returns of the two funds differ at the 5% level of statistical significance. Assume the underlying distributions of returns are normal and population variances are unknown. Fund A mean return 12.50. Fund B mean return 14.10. Difference 1.60. Standard deviation of differences 3.20. Degrees of freedom 15. Critical t-statistic at 5% level 2.131. Null hypothesis H0. Mean difference of returns equals 0. Based on the paired comparisons test of the two funds, the most appropriate conclusion is that H0 should be A rejected because the computed test statistic exceeds 2.131. B failed to reject because the computed test statistic exceeds 2.131. C failed to reject because the computed test statistic is less than 2.131. An analyst is examining whether the volatility of a bond portfolio's monthly returns is less than 4%. Which of the following best represents the hypotheses to be tested? A. H0. Variance is greater than or equal to 0.16%. B. HA. Variance is less than 4%. C. H0. Variance is less than or equal to 0.16%. A pooled estimator is used when testing the difference between two population means under the assumption of equal variances. The decision rule compares the test statistic to the critical values, but the pooled variance formula applies only when variances are assumed equal. Option B. When variances are not assumed equal, a separate variance, Welch's t-test, is used instead of a pooled estimator. Option C. Testing the difference between two population variances uses an f-test, not a pooled estimator. The samples are dependent, related, because the same individuals are measured before and after the program. Because the data involve a common element, the analyst, the observations are paired, making the paired comparisons test the correct statistical choice. Option A. A two-sample z-test or t-test is inappropriate here because it requires independent samples, which contradicts the fact that the same analysts are being tested twice. Option B. The chi-square test for independence is designed for categorical data, whereas forecast errors are numerical or continuous values. The chi-square statistic is the specific test required for hypotheses concerning the variance of a single normally distributed population. It is explicitly distinguished from t-tests, which are the theoretically correct choice for tests concerning population means. The use of chi-square to tests of independence involving categorical data. T-tests are the most appropriate choice when the goal is to compare means while population variance is unknown. There is a clear hierarchy for selecting test statistics. Means use t or z distributions, while a single variance uses chi-square, and the equality of two variances requires an f-test. This confirms that the chi-square test is uniquely applied to single population variance, rather than differences between means. The f-test is explicitly identified as the appropriate tool for testing the equality of variances between two independent samples. Test statistic. It functions by calculating the ratio of the sample variances, which follows an F distribution. Option A. The z-test is designed for hypotheses concerning population means or proportions, not variances. Option C. The chi-square test is used for the variance of a single population or for categorical data independence, making it inappropriate for comparing two separate variances. T or Z are for means, chi-square is for a single variance, and the f-test is the unique requirement for comparing two variances. All tests for means share a common structure. The difference between the observed and hypothesized values, the numerator divided by the standard error, the denominator. Paired comparisons test is that the samples are dependent or related, matched observations, which is explicitly stated in the problem. A two-sample t-test is inappropriate here because it requires independent samples, which would involve different formulas like pooled variance. Instead of comparing two group means, you must calculate the average of the individual differences between the pairs. Standard deviation of differences. The calculation uses n-1 degrees of freedom in the denominator to find the variability of those specific differences. Standard error. This is the final denominator calculated as the standard deviation of the differences divided by the square root of the number of pairs, which leads to the correct result of 1.11. Samples are independent and the population variances are assumed equal, which the sources state requires a pooled estimate of the common variance. Since the population variances are unknown, the t-distributed test statistic is the theoretically correct choice. The numerator correctly represents the difference between the observed sample means. The denominator, standard error, uses the pooled standard deviation and accounts for both sample sizes n1 and n2 to determine the estimated variability of the difference. The calculation results in 0.805, which rounds to 0.81, option B, demonstrating the application of the pooled variance formula provided in the curriculum. The samples are independent, drawn from normally distributed populations with unknown but equal variances. Under equal variance assumption, the pooled variance must be used. Option A is for unequal variances, Welch's t-test, and option B is for paired samples. Equal variances plus independent samples, pooled variance 2-sample t-test. Independent samples, equal variances, pooled variance t-test. Independent samples, unequal variances, Welch's t-test. Dependent are paired samples, paired t-test. The choice of tests depends on whether samples are independent or paired, and whether variances are equal or unequal. When testing a claim about a single population, standard deviation, or variance, the sources explicitly require the use of the chi-square test statistic. For this specific test, the distribution is characterized by n-1 degrees of freedom, 23 in this case. Remember to square the standard deviations to convert them into variances before multiplying by the degrees of freedom in the numerator. The final calculated value of 20.7575 serves as the test statistic, which is the quantity used as the basis for deciding whether or not to reject the null hypothesis. For dependent samples, the test evaluates the mean of the differences, 1.60, rather than the difference between two separate means. Standard error calculation. The denominator, 0.80, is derived correctly by dividing the standard deviation of differences by the square root of the sample size, which is the standard procedure for a paired comparisons test. Test statistic result. Following the t-distribution formula for mean differences, the resulting computed statistic is 2.00. The decision depends on whether the calculated statistic is more extreme than the critical value. Because the calculated value, 2.00, is less than the critical threshold, 2.131, there is insufficient evidence to reject the null hypothesis. The result is a fail to reject H0, aligning with the curriculum's requirement to never accept the null hypothesis. Volatility refers to standard deviation. However, the hypotheses are stated in terms of variance, which is standard deviation squared, 0.16%. The suspected or hoped for condition, less than 4%, is always set as the alternative hypothesis, HO, while the null hypothesis, H0, is the statement the researcher wants to reject. Option B is incorrect because it fails to square the standard deviation, mistakenly using 4% for both volatility and variance. Option C is incorrect because the null hypothesis must be the opposite of the researcher's suspicion and must always contain the equality sign. Collective exhaustiveness. Together, H0 and H must cover all possible values. If HO is less than, H0 must be greater than or equal to. Topic: Parametric versus non-parametric tests. A non-parametric test is most appropriate when the A data can only be expressed in terms of order or relative ranking. B populations are normally distributed with known variances. C test statistic is based on a Z distribution with a large sample size. In which of the following cases would a non-parametric test be most appropriate? A. An analyst has survey responses ranked from most satisfied to least satisfied. B. A sample of stock returns is normally distributed with known variance. C. A test of differences in means is valid only if multiple population assumptions all hold true. An analyst is comparing the quarterly returns of two equity strategies over the past 10 years, 40 observations each. The returns for both strategies are non-normally distributed. To test whether the mean return of one strategy is greater than the mean return of the other, the analyst can use a parametric test only, B. A non-parametric test only, C. Both parametric and non-parametric tests. An analyst is choosing between a parametric t-test and a non-parametric Wilcoxon rank sum test. She has a sample of 50 monthly returns from an equity index. The data are measured in percentage terms, appear approximately symmetric, and pass a test for homogeneity of variances. Which test is most appropriate to use in this situation? A. Non-parametric test, because the sample size is sufficiently large. B. A non-parametric test, because returns are financial data and rarely normal. C. A parametric test, because the data meet the necessary distributional assumptions. When working with a large random sample, which of the following types of data are least appropriate for analysis using non-parametric tests? A. Survey ratings, satisfied, neutral, dissatisfied. B. Up or down classifications of stock price changes. C. Monthly portfolio returns expressed in percentages. Non-parametric tests are most appropriate when data are ordinal or rank-based, order, relative ranking categories. They are also useful when data are non-normal, skewed, or contain outliers, and when assumptions of parametric tests are violated. Non-parametric tests compare ranks, medians, or distributions, not means. Option B. Normal distribution with known variances is the ideal case for parametric tests, like z-tests. Option C. Large sample size with z-distribution also points to parametric tests, often justified by the central limit theorem. Parametric tests assume specific distribution, usually normal, use interval or ratio data, more efficient if assumptions hold. Non-parametric tests do not rely on distribution assumptions, use for ordinal or categorical data, or when parametric assumptions are violated. Non-parametric tests are designed for ordinal or ranked data where intervals are not meaningful. In the survey case, satisfaction levels are ranks, so a non-parametric test is appropriate. Non-parametric tests analyze ranks or signs, not numerical parameters. Option B. Normally distributed data with known variance, parametric test, z-test. Parametric tests are preferred here because they have more power when assumptions hold. Option C. Highlights parametric test assumptions, but does not itself justify non-parametric use, unless those assumptions are violated. Use non-parametric when distributional assumptions are violated. Outliers distort parametric measures. Data are ordinal or categorical. Hypothesis does not concern a parameter. Non-parametric tests are robust when parametric assumptions fail. Parametric tests rely on distributional assumptions, use full data values, higher statistical power. Non-parametric tests, minimal assumptions, often distribution-free, use ranks or signs. More robust but less powerful. Even though the returns are non-normal, the sample size is large, n equals 40 per group. By the central limit theorem, the sample mean is approximately normal, so a parametric test, two-sample t-test, can still be used. A non-parametric test, Whitney U, is also valid since it does not require normality. In large samples, both parametric and non-parametric tests are applicable. Option A, saying parametric only ignores the fact that non-parametric tests are valid regardless of distribution. Option B, saying non-parametric only ignores the fact that parametric tests can be applied here due to the central limit theorem. The data are interval or ratio, percentages, appear symmetric, and pass the equal variance test. With a sample size of 50, the central limit theorem supports normality of the sample mean. All assumptions for a parametric t-test are satisfied, making it the most appropriate and most powerful choice. Option A, large sample size alone does not justify using a non-parametric test if parametric assumptions are met. Option B, while financial returns can often be non-normal, in this case, the data are symmetric and meet assumptions, so parametric methods are valid. Monthly portfolio returns and percentages are interval or ratio data. With a large random sample, the central limit theorem supports parametric tests, like the t-test. Parametric tests are more powerful, so non-parametric tests are the least appropriate here. Option A, survey ratings are ordinal data, so non-parametric tests are appropriate. Option B, up or down classifications are categorical data, often tested with non-parametric methods. For example, runs test. Parametric requires continuous numerical data. Non-parametric is for ranks or categories. Small non-normal samples, non-parametric. Large samples with interval data, parametric. Parametric tests rely on assumptions and use full data values, higher power. Non-parametric tests make minimal assumptions, often using ranks or signs. More robust.